Okay, so here we are. I'm Michele Lombardi from the University of Bologna. This is a joint work with Alessio Confetti, who is in this room, and with Michele Andriano. I'm going to talk about the methods to tackle the cyclic scheduling problem without resorting to ad hoc, to special purpose algorithms, but just using commonly available constraint solvers. So, first step, what is cyclic scheduling? Say we want to build a skyscraper. What do we have to do? We have to build a floor, we have to extend the pillars, then make the walls, then we add the wires and pipes and whatever is left. We just have to do this a bunch of times. Once for each floor. So this is the essential part in cyclic scheduling. There is a small project you have to repeat indefinitely over time. Something more. You may notice that we have a poor chance to build the second floor if we don't extend the pillars to the first floor first, right? So basically we have a cyclic dependency here. Not just a cyclic dependency, but a cyclic dependency with a delay. This one number here means that the next execution of A0 must wait for the current execution of A1 before starting. So formally we have this. This is a normal precedence constraint in cyclic scheduling, which tells us that A1 at execution K must wait for the end of A0 at execution K. This is this error. This is a precedence constraint with a delay, and the delay appears here. This tells us that A0 at execution K plus 1, which is the next one, must wait for the end of A1 at execution K, which is the current one, right? So those are cyclic dependencies and delays. We have precedence constraints. We can assume to have renewable resources and a fixed requirement for each activity is already complex enough. And one more thing, usually we want to build for this kind of problems a periodic schedule. We don't want obviously to choose the start times for now to infinity, so we decide a fixed set of start times and we repeat them with a pattern. Basically, we have this relation. The start time of AI at iteration k is equal to the start time of AI at iteration 0 plus k times lambda. Lambda is a period. How does it look like? Our time horizon. We build a schedule for the first execution, which means that we assign a start time to each variable. Then this is the make span of the schedule, and then we can repeat it. We repeat it, in this case, every 4 time units, which means that 4 is our period. The goal in this kind of problem is not to minimize the make span, but it is to minimize the period. Because the smaller the period, the more floor we can build in a fixed amount of time. Okay. So the obvious question is, how do we solve this stuff? And I'm talking about how do we solve this stuff with constraint programming in this case. Something that we can do is using special purpose constraints and special purpose search algorithms. This works, we've worked on that, and you can do nice things. The problem is that those algorithms are not widespread. They're not so easy to get. So it would be very interesting if this class of problem could be solved by using traditional constraint solvers. So it is possible to reduce the stuff to something that we already know. The simplest thing that we can do in this direction is building a schedule for the first execution, forgetting about cyclic dependencies, then we repeat this stuff every make span. And this works, we get a correct schedule in this fashion. There is one big problem, that we are wasting a lot of resources. And this is a huge issue, because usually in cyclic scheduling is a way to exploit the availability of a lot of resources. We have a lot of resources, but we want to exploit them by building a pipeline. In this case, your pipeline will be very poor. This kind of approach is called block scheduling. This technique is called blocking. We can be smarter than this. We can, for example, take our original graph, and we can try to build a larger graph which represents a number of consecutive executions of the project. So, for example, we can make a copy, and then we translate the original dependency with a delay into a set of dependencies. This stuff here is not so difficult to obtain in practice. You can do it very efficiently, and represents 2 executions of our original project, right? So now we do the same stuff as before. We build the schedule for the 2 iterations, and we repeat every make span. So we get a periodic schedule. It is still correct. It is better than the previous one because now we are allowing some iterations to overlap. The iterations captured in our graph can overlap over time, and we can better exploit the resources. The big drawback is that we have to solve a much bigger problem, because we have to assign the start times to all those guys instead of just 4. This is more difficult. There is something more. This kind of schedule is not really periodic. It is okay, it is periodic with a pattern. Sometimes you just don't want to do this, because for example you have just a little memory to store your schedule, and so you care about having it small. So this is the main question of this talk. Is it possible, really possible, to use a traditional constraint method to solve this class of problems? So we thought it was impossible actually. We started to prove it, and we came to the result that it is instead possible. I will show you why. So the basic trick is this one. You fix the period. You can still optimize it by doing a binary search over the possible period values, but if you do this, you get two important results. The first one is this. Let's look at precedence constraints. This is a precedence constraint with a delay, right? This is the general case. If we plug in the periodicity, we get this. We can decompose the start time in this sum and the end time in this other sum. We may notice that those terms cancel each other, and so we get this, which tells us two important things. The first one is, if the precedence constraints are satisfied for execution 0, then they're satisfied forever in a periodic schedule. The second important thing is that if lambda is fixed, this is a linear constraint. This is just a precedence constraint with a time length, nothing special here. We know how to deal with this stuff. So this is the first important result. Basically, in our original graph, we translate the delay into a temporal time length. Okay, so what about the precedent, the resource constraint, right? This is probably going to be a little more complex, and in order to tackle those, we are going to borrow something from the unfolding technique, the idea of growing the graph. So what we do is representing the additional executions of the activities as additional activities. And we do this, for example. We introduce some replicas. But unlike in unfolded scheduling, we post synchronization constraints between the start times of those guys, of the additional activities representing multiple executions of the original ones. This is just a start-to-start precedence constraint with minimal and maximum time length. Very easy. So, basically, the original precedence constraints are guaranteed by those guys here, and we don't need anything more here. So, the replicas are just built for the sake of the satisfaction of the resource constraint. The obvious question is, how many replicas should we make? At some point, we cannot have infinite replicas, right? So, if we look at the periodic schedule, and we swipe the whole length of the next span, we may notice, in this case for example, that we never have more than 3 colors at the same time. In these representations, the colors represent different executions, right? This means that we will never have more than 3 different executions overlapping in time. How did we get this number? We took it by taking the next span, dividing it by the period, making a seal, and then you get 3. Of course, if you are searching for an span, you don't have access to this, but you can safely replace it with an upper bound, and still you get an upper bound on the maximum number of possibly overlapping executions. In this case, since this is 3, we know that we will never need more than 3 replicas. So we can build this. It looks complex, but it should be relatively easy to understand, right? This is a This is a resource constraint project scheduling problem with timelines. We need that ingredient. And this is an equivalent representation of a cyclic scheduling problem with a fixed period. And this is already a very nice result, because it means that you can actually use constraint method to solve the cyclic scheduling problem with no fancy addition. There is one big issue, still one big issue, and which is this one. If the make span upper bound is much greater than the period, then you're going to need a lot of replicas. A lot of replica means no more start times to be decided, because we have the synchronization constraint, but it means a lot of overhead. In practice, your approach will not be very effective. Can we do something smarter? Yes. Okay, so let's look at the periodic schedule again. Let's narrow our focus to an interval which is as long as the period. In this case, 4 10 units. So let's look at a single activity. In this case, it is A2. So look at the cumulative resource usage due to all executions of the activities appearing in this period. It is 1 here, then 2 here, and then 1 again. So in practice, we get this. In this kind of shape, you can recognize 2 parts: a base, which is always as long as the period, and a peak, which is always shorter than the period. The length of this guy and the height of both those guys can be computed easily if you know the period value, which is exactly our hypothesis. So what do we do now? We can take care of the base consumption by simply reducing the resource capacity. And we do this. In order to take care of the peaks, part of the peak part of the consumptions, we just make a schedule of the peaks instead of making a schedule of the activities. We compute this peak for each activity, and then we schedule them instead of the activities. And we get something like this. What is the nice part? What is the trick? What is the trick here? Since all the peaks must start in an interval which is shorter than lambda, and since the peak duration is necessarily shorter than lambda, the mean span of this stuff will be shorter than 2 times lambda. Which means, if we take our previous technique, that we will only need 2 replicas. 2 replicas will be enough. So we start from this, and we just need a replica, and the synchronization of constraints, of course. Obviously, there is a catch, and the catch is that those guys here are no longer representing real activities. Those are the peaks, right? We can still deal with the precedence constraints, but we can cast them into linear relations. But in order to do this, we have to introduce additional variables, additional decision variables. So this is basically the drawback of this kind of approach. I won't go into details because we don't have time. I'm representing those weak precedence constraints with error here. This is our second representation, which is not a classical scheduling problem, but still those are precedence relations, are linear constraints, right? So you can solve this stuff with most available constraint solvers. Okay, some results. This is a quality comparison. Here we have an instance size. Those are average values over 10 or I can't remember how many instances. This is blocked scheduling, and we are using it as a baseline. Those are unfolding approaches with unfolding factor 3 and 5 respectively. And those are the new formulations. Here what we are doing is this. We are doing binary search on the period values. For each fixed value of the period, we solve a subprogram with a time limit. And in practice, we are solving the problem in a heuristic fashion. We cannot guarantee optimality in this way. And we'll say something about this later. So the good news here is that the blue lines are always, more or less always, under the red lines, which is good, since we are competitive with the unfolding approach as concerning quality. We have to slightly better. If you look at the time, the picture is even better, because now the blue lines clearly grow much slower than unfolding. So the new approaches are actually more scalable than the existing state of the art. So, result, we have introduced 2 new formulations for cyclic scheduling problem that allow them to be tackled with traditional constraint tools. The new formulations are effective in finding good schedules, are pretty fast. There are still things to do. One is comparing the new approach with ad hoc methods, of course. We are going to do this. Then, since we have additional variables in the quasi-LCDSP representation, it's fully advisable to have a better search strategy for this kind of problem. And the optimality proof is a pain. It takes forever to complete. So you can get very good schedules quickly, but proving optimality is very difficult in general for cyclic scheduling problem. Okay, I'm done.